Now let's talk some about matrix functions. Here we'll first define what a matrix function is, but mainly we'll talk about several examples of matrix functions, some of which you've seen before and some of which are very common in practice. To start off with, you may be familiar with functions like this, f of x being a function that returns x squared, so f of x is equal to x squared. The way we write this is we say f is a function that maps r to r because f takes as input scalar values and produces scalar values. It just takes a single scalar value and then squares it, which is also a scalar value. When we talk about matrix functions, we can now talk about functions that have matrix inputs and outputs. And the way we write that is we write f is a function that takes as input, say, an m by n matrix, and outputs, say, a p by q matrix. Now, of course, this is just defining the size of the inputs and outputs of f. To actually define a function, we need to say what do each of these elements actually equal in terms of the inputs. But this is how we write a basic matrix function. Now it turns out we've already seen several examples of matrix functions. For example, the transpose can be viewed as a matrix function. If we define f of a to be equal to a transpose, then f is a function that takes m by n matrices as input and outputs n by m matrices, because the transpose switches the rows and columns of a matrix. Similarly, we could define a function, f of a being equal to a inverse. This would be a function that takes as input n by n matrices and also outputs n by n matrices, because the inverse of a matrix, of an n by n matrix, is also n by n. So this would be another example of a matrix function. Something like multiplication is also a matrix function. For example, we could define f of x for x being here a vector in Rn, because x has to be in Rn in order for this multiplication to make sense. But if we define this function as f of x equals a times x, for a being m by n, then this function would take as inputs vectors in Rn. So we write f here as mapping from Rn, and the output of this function would be the product. Remember, a here is m by n, x is n by 1, so the output of this function are vectors in Rm, and so f maps from Rn to Rm. The trace is another example, which we haven't seen so far, but the trace is a very common matrix function. The trace, which we'll write tr, takes as input square n by n matrices and produces a real scalar value. The trace of A is just defined as the sum of all the diagonal entries of A. So we have a matrix A. The trace would ignore all the entries but the diagonal ones. Just sum these entries together and return that sum. Now, some important properties of the trace, which follow directly from this definition, are first of all, the trace of A is equal to the trace of A inverse. Right? Inverting a square matrix will not change the elements on the diagonal, so the trace is equal to the trace of the transpose. Another very simple property is that the trace of A plus B is just equal, of course, to the trace of A plus the trace of B. Doesn't matter if we first add the matrices and then sum their diagonal elements, or sum their diagonal elements and then add those two things. And finally, the trace of A times B equals the trace of B times A. This property is less obvious, and in fact this even holds if A and B are different sizes. So here A is m by n, and b is n by m. Now they have to be the right size so that both these two products here, a times b and b times a, are both square. But here, because the trace is only defined for square matrices, but here a times b would be an m by m matrix, whereas b times a would be an n by n matrix. Yet the traces of these two terms, and it's pretty easy to show this by just substituting in the definitions for matrix multiplication here, these two terms are actually equal. Norms are another very important category of common matrix functions. We'll particularly talk about vector norms. So these are functions that take as input a vector in Rn and output a scalar value. In particular, a norm is a function with these three properties. So any function that has these three properties is a norm. First of all, f of x, then any norm, is always greater than 0, and it is greater than or equal to 0, and it is equal to 0 if and only if x equals 0. These two properties are called positivity and definiteness. Another important property, which is called homogeneity, is that if we take a scalar value a and we take the norm of a times x, this is equal to the absolute value of a times f of x. So multiplying x by a scalar value scales that norm by the absolute value of that scalar. And finally, the third property is called the triangle inequality. And this says that the norm of x plus y for two vectors, x and y, that are of course the same size, otherwise we couldn't add them together, the norm of this sum here is less than the sum of the norms. And the reason this is called a triangle inequality is you can think of norms kind of like distances. And we'll see in a second that actually a very common norm is what we typically think of as distance. So if x and y are two vectors, say in 2 dimensions, so we can draw them both as arrows, and say this is x, and if this vector here is y, then x plus y would be this vector here. What the triangle inequality says is, in some sense, the size or the length of this vector, the combination of these two, is less than the added length or size of the two vectors. If we add this length and this length, it's bigger than this length. That's kind of the intuition and why it's in fact called the triangle inequality. Now there are a few common examples of norms that you'll see very often. The first of these is the L2 norm, which is written as x in these double lines here, subscript 2. And this is equal to the square root of the inner product of x with itself. And remember, the inner product of x with itself would just be the sum from I equals 1 to n of all the entries of x squared. So a common usage of this in, say, 2 dimensions would be this norm here corresponds very naturally to distance, right? So if x was an R2, then the 2 norm of x would just be the size of x, right? It'd be x1 squared plus x2 squared, and then the square root of all that, which is a very natural notion of Euclidean distance. And this is actually just the definition of Euclidean distance in however high dimensional space you want. This one is very common, and the properties of the norms are quite natural for something like the L2 norm. But it also turns out there are other possible definitions of norms, and here it's a little harder to show the different properties. They're not that hard. But here it might not seem quite as intuitive that these are also somehow measures of the length of a function, or the length of a vector, rather. But in both cases, these actually are norms, and you can prove all the previous properties about these functions. The L1 norm, denoted subscript 1, is just the sum of the absolute values of these terms, of the xi terms. And the infinity norm is just the maximum magnitude, or rather the absolute value, of the largest magnitude element in X. Finally, the determinant is another function that comes up often in linear algebra. We'll denote it det, or det, and this is a function that takes as input n by n matrices and outputs a scalar value. Sometimes this is also denoted with these little vertical lines here, so we might write something like this for the determinant of A, but we're not going to do that in these videos. We're going to write this as det of A, because sometimes the notation of these two lines is also used for absolute values, and that can confuse things somewhat. Now there are many ways of defining the determinant, and in fact we'll give a little bit more rigorous definition on the next slide. But one intuition for the determinant is that if you look at these vectors that make up the rows of a matrix here, so A1 here is going to be the first row of A, and A2 is the second row of A. If you think of these rows as vectors in space, so here I'm just drawing a two-dimensional space, so we're talking about a matrix A in R 2 by 2. If you treat these as vectors and then form the parallelogram, in higher dimensions it has a different name, but in 2 dimensions it's a parallelogram. If you form the parallelogram from these two vectors, so this is A1 here, I'm going to add on to it this term here, which is A2. If you form this parallelogram and then look at the area inside of it, the absolute value of the determinant of A is actually equal to the area of that parallelogram. We're not going to prove that. It's not that hard to show, but that will hopefully give you some intuition about what the determinant is. It's some measure of area, or in the higher dimensional cases, it's a measure of volume of the inside of the shape formed by the rows of A. A little bit more formally here, we can also actually define the determinant in terms of three properties. First of all, the determinant of the identity is equal to 1. We'll just define that, because the identity in some sense is the unit for a matrix. Secondly, if we take one of the rows in the determinant, one of the rows in the matrix A, and take the determinant of this thing, that scales the determinant by the scalar t. So we're scaling one of the rows by t, that will scale the entire determinant by t. What that also means is that if we scale all the rows by t, for example, then we would actually be scaling the whole thing by t to the n. And finally, swapping rows will negate the determinant. So if we take A1 transpose being the first row of A, and A2 transpose being the second row of A, and we swap these two rows, that will actually negate the determinant. And the fact that the determinant actually captures the volume of the shape formed by these rows is actually a very natural consequence of these three rules. And you can define all the other properties of the determinant in terms of these three rules. These oftentimes aren't that intuitive, though, and so we'll finally end by just describing a few more properties of the determinant which hopefully add a little bit more insight into what it is. First of all, the determinant of A is equal to the determinant of A transpose. Transposing matrix will not change its determinant. Remember, we're talking only about square matrices that have determinants here, and so we can take the transpose of that matrix. That's still a square matrix. The determinant of A times B is equal to the product of the determinant of A times the determinant of B. Third, and this is a very important property relating to matrix inverses, is that the determinant of A being equal to 0 is equivalent to A being singular. Remember, this means A being singular means A does not have an inverse. So A does not have an inverse if and only if the determinant is equal to 0. And finally, the determinant of the inverse of a matrix is just equal to 1 over the determinant of A. This also clarifies a little bit, or maybe not clarifies, but at least reinforces the idea that if the determinant of A is 0, then A really can't have an inverse because the determinant of the inverse would have to be infinite. Now, it's not at all obvious that the properties from the previous slide actually imply all these things, but they in fact do. And they also imply a formula for the determinant, but that itself can be quite complex, and even computers don't really compute it in the typical closed form you see for a determinant. Nonetheless, you will see determinants a lot, and so it's good to have some basic intuition of what this is symbolizing and some basic properties of these determinants.